For a long time, some people have thought that pairs of identical twins don't just look alike, but have many similar instincts. Some twins even claim to have a telepathic ability to communicate with each other. For instance, a number of cases have been reported where one twin has been aware that some experience is happening to the other, even though they may be a great distance apart. Well, we've reached the point in the course where we're looking at hypothesis testing. So today, in the studio, we're going to use the ideas you've already met in the unit to help us carry out a test for telepathy. Behind me is the area where we'll carry out the experiment. All we need now are the twins. They're the Wilson twins. This is their mother, Joy. Now, I know, Joy, their names are Catherine and Jennifer, but can you tell me which one's which?
Yes, Catherine is the one in the brown, nearer to you, and Jennifer's here in green, next to me.
Right. Now, have you noticed any sort of telepathy between them at all?
Yes, I've noticed that several times they've reported having the same dream, particularly if they've been rather poorly and had a disturbed night. They've often ended up having the same sort of dream.
Right. Well, let's put that to the test, shall we? Jennifer, if you can go with Mummy and sit at that table, and Catherine, you come with me, and I'll tell you what the experiment is. Now then, we've got some cards here, and what I want you to do is put these cards into this rack one at a time. And to tell you which card to put in, you're going to use this spinner. Okay, so spin the spinner, and we'll see what happens. Okay, now, you see that, and you pick up that card, and as you pick it up, press that button, and that tells Jennifer you've got the card.
Now, you see the red light? That's your sign that you've got to start thinking about which card you're going to put in the rack.
Okay, and when you've looked at that for a little while, you put it in the first place in the rack. Okay, now what you've got to do is to keep doing that. The spinner, pick up a card, press the button, think about it, and fill in the next space, and keep doing it until all 15 of these spaces are full. Okay? Now, let's put that back then, and we'll do the experiment for real. So you start now by spinning the spinner.
While they're doing the experiment, we're going to derive a method of analysis by which we shall be able to determine whether there is any evidence for telepathy between these twins. If they don't possess telepathic powers, then whenever Catherine holds up a card, Jennifer has a 1 in 5 chance of guessing it correctly. And with a 1 in 5 chance, each guess represents a Bernoulli trial with probability 1/5. And as you've seen, there are going to be 15 trials. So if there's no telepathy, the total number of correct guesses will have a binomial distribution with n equal to 15 and p equal to 1/5. But what if telepathy does take place? Then, with each trial, Jennifer has a greater than 1 in 5 chance of guessing correctly. And the total number of correct guesses will still have a binomial distribution with n equal to 15, but with some value of p which is greater than 1/5. Now, like most people, I'm skeptical about the existence of telepathy, and I'm not going to believe in it unless I see some strong evidence. In other words, my null hypothesis, my status quo belief, is that telepathy does not exist, which in the context of the experiment going on at the moment says that p equals 1/5. Jennifer is simply guessing at random. The alternative hypothesis, which corresponds to the rejection of my current belief, is p greater than 1/5. So here we have the beginnings of a hypothesis test. If x is the number of correct guesses, then x is binomial 15p. Our null hypothesis h0 states that p equals 1/5, and our alternative h1 states that p is greater than 1/5. But for what values of x should we reject the null hypothesis?
Here's the binomial distribution for n equals 15, p equals 1/5. And to represent a distribution under the alternative, we've used p is a quarter. Look at a specific value, say x equals 7. The probability under h1 is 2 to 3 times as large as the probability under h0. You can see that more clearly if we magnify the vertical scale for this part of the picture. But we've only looked at one value for x. Let's look at this ratio for all the values of x from 0 to 15. We'll plot them on a graph. You can see that for larger values of x, the ratio is bigger, and for some values, it goes off the scale. Now, what's really interesting about this is to see whether this will happen for all possible values of p under h1. Will the points always continue to rise? So we'll start with p close to 1/5, so that the ratios are all approximately 1. Then, as we increase p, it just gets steeper and steeper, and very soon, most of the values are off our scale. It's now quite clear for all possible values of p under the alternative hypothesis, the rule is going to be reject h0 if x is sufficiently large.
Here again is the distribution of x, the number of correct guesses, under h0. And as we've just seen, we want to concentrate on what happens in the right-hand tail. The question we have to ask ourselves is how much of the right-hand tail shall we put in the critical region? Let's consider the extreme cases first. As we move down from 15 to 11, these probabilities are all practically 0. We can see a very small probability at 10 on this diagram, but the accumulated probability from 15 down to 10 is still only 1 in 10,000. Now, what does this probability mean? If we were to take this to be the critical region, it's the probability of rejecting h0 when we shouldn't. Should we stop here? Well, if the twins did achieve as many as 10 correct guesses, I, for one, would be strongly inclined to reject the null hypothesis, even though there is a small chance of my being wrong. That, you'll remember, is what we call a type 1 error. Suppose, then, we take the critical region to be 9 and above. The tail probability is 8 in 10,000, which is still extremely small. What about 8 and above? It's 0.0042. That's about 1 in 250. And of course, the larger I make the critical region, the larger this probability will be. And I have to decide just how large a probability I'm willing to risk. To make this decision, I need to consider the consequences of making a type 1 error. If I did reject h0 falsely and told the world that I had found a pair of telepathic twins, then my reputation would suffer, because sooner or later it would be shown that I had blundered. And the girls' privacy would be further invaded as they became the focus of more scientific investigation. In other circumstances, I might not want to take a risk greater than 1 in 250, and so my critical region would now be defined. But what's my reputation? Here, I'm quite happy to increase the probability to about 1 in 20, 5%. So let's continue. Now, a critical region of 7 or more has a probability under h0 of 0.018, about 1 in 55, which is still a bit small for my purpose. But 6 or more has a probability of 0.061, about 1 in 16, and that's about as near as I can get to my desired 1 in 20. This probability is, of course, the size of the critical region alpha, which you've met in the text. What that means in the context of the experiment is that if Jennifer guesses 6 or more cards correctly, we shall conclude there is evidence of telepathy. While if she guesses between 0 and 5, there's nothing to support such a conclusion. So let's see how well they've done.
Well, they've just finished, so let's compare the results. So I'll take Catherine's cards over here so that we can compare them with Jennifer's. So I'll put that there. Joy, could you give me Jennifer's? Lovely. Thanks very much. OK. So these are the cards that Catherine picked, and these are the ones that Jennifer guessed. So let's see how many she got correct. No, that's no good. No. 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 There's one. There's two. There's two pluses there, that's three. So altogether, they got 3 cards correct. And since this doesn't fall into the critical region, then we have to deduce that there's no real evidence that telepathy has taken place.
Of course, there is another type of error that can occur besides the type 1 error, and that happens if we persist in believing H0 when in fact telepathy is present. You should recognize that as the type 2 error. Now we're going to talk about something that's related to the type 2 error. It's called the power of the test. And it's in fact the probability of rejecting H0 when H0 is false. And so is obviously something we would like to be as large as possible. Since this is a new idea to you, let's see what it means. Let's assume that the twins are capable of telepathy with a probability of, say, 0.35 of a correct guess. Here's the binomial distribution with n equal to 15 and p equal to 0.35. So if they are telepathic with this probability, the number of correct guesses is an observation from this distribution. Any outcome between 0 and 5 correct guesses would lead us to go on accepting H0 and to commit a type 2 error. However, for any outcome of 6 or more cards correct, we would properly reject H0. So the power of the test is the sum of all these probabilities, which in this case comes to 0.436. So even if the twins are telepathic and do have a probability of 0.35 of a correct guess, we have a greater than even chance of not detecting it. But for the sake of example, we've chosen a particular value of p, 0.35, whereas under the alternative hypothesis, p may take any value provided it's greater than 1/5. So the power varies with p. You can see that as p increases, so does the total probability in the critical region. That means the power is a function of p. So let's look at its graph. It's plotted from p equals 1/5 up to p equals 1, at which point the power is 1. P is 1 means that a correct guess is certain. So the power is 1 and detection of telepathy is certain. And at the other end of the graph, when p equals 1/5, the power is in fact the size of the critical region, 0.061.
So unless the twins have a probability of a successful guess, which is well above 1/5, then there's little chance of us detecting telepathy anyway. Now, of course, no one would actually base a test of evidence of telepathy on as few as 15 guesses. So what we'll do is let the twins continue the experiment, and at the end of the program, we'll re-examine the evidence.
So far, we've seen that in an experiment of 15 trials, the girls scored 3 successes, a result that did not lead us to reject H0. And on the basis of the test we devised, nor would we have rejected H0 if they had scored 5 or 4, 2 or 1, or even no correct guesses. But just a moment. Suppose they had actually got no guesses correct. Might one not suspect that perhaps some anti-telepathic power was at work? In fact, those researchers who do conduct experiments for telepathy often regard an abnormally low number of correct guesses as being significant, as well as an abnormally high number. It could be, for instance, that one of the participants deliberately or subconsciously suppresses the correct image and replaces it with an incorrect one. In the formal terms of our test, this would mean replacing our one-sided alternative hypothesis with a two-sided one. That is, p is not equal to 1/5. As you will recall from the unit, the consequence of this is to change the critical region from being solely in the right-hand tail to being partly in the right and partly in the left. And the simplest way of dividing the size alpha of the critical region is equally between the two tails, or as nearly equal as possible. Let's again choose alpha to be approximately 5%, but now with about 2.5% in each tail. And let's see how closely we can achieve this. We'll start with the left-hand tail. Under the null hypothesis H0, x is binomial 15 1/5. We want to consider from the left the values of x, 0, 1, 2, and so on, until we find a cumulative probability of about 2.5%. That's 0.025. So let's start with x equals 0. Under H0, this has probability 0.035, which is already greater than our required value. So we need consider no further points on the left, and the critical region at this end consists only of x equals 0. What about the right-hand tail? We saw earlier that the probability of observing a value greater than or equal to 6 is 0.061. This is now obviously far too high. So let's move this part of the critical region out a little to x greater than or equal to 7. This region has probability 0.018, which is as near as we can get to 0.025. And in fact, in conjunction with x equals 0, gives a complete critical region with size 0.035 plus 0.018, that's 0.053, quite close to our desired 5%. Notice that the twins' result of 3 successes does not fall in this new critical region, and so would not be judged significant, even with this two-tailed test. But of course, we could be making a type 2 error and persisting in accepting H0 when we shouldn't. So really, we ought to see what the power function looks like for this two-sided alternative hypothesis.
This is the binomial distribution under the null hypothesis, with the probability of a correct guess equal to 1/5. Its critical region is 0 and the integers 7 to 15. Now let's look at the alternative hypothesis. We'll change p from 1/5 to 1 and plot the power curve. Again, the power starts with the same value as the probability of making a type 1 error, and again it climbs to 1 as p approaches 1. However, we can now look at values of p below 1/5, since the alternative hypothesis also tests for a probability of success below 1/5. The power climbs again and rapidly approaches 1 as the probability approaches 0. Now let's compare this power function for the two-sided test with the power function we obtained before for the one-sided hypothesis test. Here they are plotted on the same graph.
This is the power function for the two-tailed test, which you've just seen. And this is the power function for the one-tailed test. You can see that the one-tailed test has the greater power over this region from p going from 1/5 to 1. And this difference comes about as the result of the inclusion of 6 correct guesses in the one-tailed critical region. In fact, the maximum difference between these two powers is quite large. It's about 0.21. Now, over this region, p from 0 to 1/5, the power function exists for the two-tailed test, but not for the one-tailed test, since in that case, p is assumed to be not less than 1/5 under both hypotheses. What is clear is that in either case, if p is in reality only slightly different from 1/5, the power is small, and hence the probability of detecting the slight presence of telepathy is small. So how can we increase our chances of detecting telepathy when it does exist without increasing the risk of detecting it when really it doesn't? You can probably guess the answer to that. We get the girls to do more trials, as they're doing at this moment. Let's see the effect on the power function of increasing the number of trials beyond 15. For the sake of convenience, we'll return to the situation where H0 is one-sided, p greater than 1/5, so that the critical region lies solely in the right-hand tail. Here once again is the binomial distribution representing the null hypothesis for 15 guesses. And here for comparison is the binomial that arises if p is actually 0.35, a possible value under H1 that we considered earlier. The critical region consists of the values x equals 6, 7, 8, and so on, up to 15. So the power is the sum of these probabilities. That is, as we've seen before, 0.436. We'll register it on this line on the right. Now let's increase the number of trials to 30. If we want to keep the size of the critical region at about 5%, we find that the region becomes 10 or above, and the power for this particular case rises to 0.642. Now we'll further increase the number of trials to 100. The critical region becomes 27 or above, and the power 0.965. But what is more instructive is to see the complete power curves for these three values of n, 15, 30, and 100. Here's the one for 15 trials, and the one for 30 trials, and the one for 100. You can see very clearly the enormous improvement that can be made by carrying out a more extensive experiment. If p is, say, 0.3, there's quite a large increase in power when going from n equal to 15 to n equal to 30, and a dramatic increase when going from n equals 30 to n equals 100. So with n equals 100, there's now an almost certain chance of detecting the existence of telepathy for a moderate increase in p over a fifth. And you can imagine that as n is increased beyond 100, the power becomes even steeper, just above p equals 1/5. Let's see now how the twins have got on since we left them to continue their experiment beyond their initial 15 trials. And Norman should have the result. Now, what I'd like to ask first, Norman, is just how many trials they managed to complete in the time available.
Well, I'm afraid we didn't manage 100, Brian, but they did do 75.
Well, now, before you tell me how many correct guesses there were, I'm going to put that number into the computer, 75, and it will then tell us what is the critical region for the test with size about 0.05. For 75 trials, the critical region is 21 or more, and we see that the size is actually 0.060. So now you're going to tell us just how many correct guesses there were.
Well, I'm afraid we only managed 16.
16 is not in the critical region, so I, for one, will go on being sceptical about the existence of telepathy.
Well, I'm sorry about that, Joy. We couldn't convince Brian, but I'm convinced that Catherine and Jennifer are two delightful girls, and I think they did the experiment very nicely. Thanks very much.
Thank you.